as Anna said, I'm Oriol Ríos. I'm finishing my PhD here at CERTEC, next building there. So really pleased to host you here. And I'm gonna present a data-driven fire spread simulator that will be a premiere because the whole system has not been presented yet. So that will be a premiere here, and benchmarking or a validation of it in the Vall-llobrega fire. Actually, it's really good that my presentation went third because the first one we saw a state-of-the-art model based on CFD modeling, which is one of the techniques to provide solutions to our problem at hand. Yeah, then this is the outline. But thing is that sometimes it's not operational or it's not operational yet. So then we have to look for some other approaches like data-driven approaches in order to provide a tool for the firefighters or emergency responders in order to use in a real wildfire. And the second talk, we saw some uncertainties in the model that are always present in the real emergency, and that will always be present. So even though if we get a super great model that can really like solve all the fluid dynamics between the trees, at some point we'll need to put the distance between the trees in order to like input data in this model. So that's like the trade-off on like going super detailed in models and still having like a well-functioning tool for fire responders. So the outline of the presentation going to be an introduction of this Q-Fire model. That's the name, how we name it. This data-driven model for forecasting fire front spread. Then I'm gonna say some words about the wind enhancement and the topographic wind enhancement it has embedded, and I'm gonna present a case study in Vall-llobrega. So as I was saying, the aim of this work is to develop a tool that can be fed with actual data on an ongoing fire in order to improve this tool, to better calibrate it, and to better give an answer to the firefighters. And the reason is that we will always have uncertainty in our cases, in our scenarios. We will never know the exact location of each tree, the exact branching, the exact combustible there, the exact weather conditions. So there is an uncertainty embedded in the scenario that should be somehow improved with data acquisition. So the aim is to use a simplified method, fed it with data, and deliver improved model. How it goes? Everything starts with data acquisition. We need some data in order to fit our model, and I'm gonna develop this point now, like all of those 4 points. So we start with data acquisition. We go for a simplified model, and that will be a two-dimension model, so not accounting for the atmosphere. Then we go with a simulation strategy. This is where we capture the true parameters that are really like driving our model. So we calibrate the parameters we don't know or we don't know exactly. And then we have an improved forecast to deliver to the fire responders. And we have this fast. So we don't have 20 hours to give the answer to the fire responders. We have 10 minutes the most to give the answer to the fire responders in order to say what's going to happen in 2 hours. And then we can go back to the loop, so update our model with new data acquisition and run the loop again and keep developing the model as the fire grows. So for data acquisition, we see, let's see if the video works. Yeah, we foresee a system that is based on infrared imagery captured for either a helicopter, either a plane, either a drone that can fly over the fire. Those are some prescribed some experimental burns, real-scale experimental burns conducted in Narcat in Australia. So that's what we have: visual image, IR image. Then we need to stabilize the video, georeference it, orthonormalize it, and then we can extract the perimeters. Extracting the perimeters is not an easy way. It's not an easy task. It's like you have a lot of image processing behind it, and we are working on that's a publication on this edge detection of this ongoing fire. Why do we foresee some aerial platforms like planes and helicopters not getting data from satellites? The thing is that we need really like a short time lag data. So we need data every 10 seconds, half a minute, 1 minute, 5 minutes most. But we do not cannot use like 2 hours lag data, because we can use it, but it's not what we foresee to use it. We foresee it to be like a good model to forecast 1 hour, 2 hour in a good resolution. So that's why for now we are not considering any satellite data. The simple model that goes behind, it's a model, it's pretty similar to Farsight. So I'm sure McFinney will identify most of the things here, because it's the same reasoning behind Farsight. And it's based on Rothermel heat balance equation, and then some Hughes expansion. This is the expansion of light for physics, and we apply it here. So each point on the fire perimeter expand as an elliptic, and then the enveloping curve is like the fire. Then we also need to put some slope in it in order to account for this slope. And then we see the result in a topographic area. So the background is a hillshade. And then we see really that even though that's a simple model, it can capture some of the terrain, for example, fire dynamics, as we see the front of the right flank of the fire is propagating towards the left, is opening as it overpass the ridge. So that's a real terrain fire dynamics captured here by a simplified model. Why do we use a simplified model? We can upgrade it, but the thing is that since we are calibrating this model with real time data, we hope that even a simplified model will already capture some of the most important physics. When you need a model, you also need to model as well. When you use a simulator, you also need to model the combustible material. Rothermel is based on like these Rothermel fuels. Afterwards, they were like completed by what is called the standard fuel model developed by Scott and Bergen. Those are 53 models that are derived for different ecosystems, and those have 27 parameters. Actually, they have 25 burning combustible parameters plus wind. So those are a lot of parameters to be optimized. So what we do here is we try to find a condensed representation of those, because you have these different time lag combustibles. So 1 hour, 10 hours, 100 hours, live combustible and live woody, live air and live woody combustibles. We need to condense them in a way that we only use one of the value per magnitude. So we ran a novel validation. That's a analysis of variance study. We ran 1 million simulations with these 53 burnable models and 16 different moisture scenarios. The moisture scenario is also like can change for each class. So we put them all together and we ran a novel analysis, so we get the influence of each parameter in trying to really like condense them. But what we saw is that there is a large spread on the dependency, because of some models do have some parameters and some others does not. There are models that does not have 100 hours time log combustible. So then the influence is different. So we keep on doing statistics, and we finally found a way of categorizing the different models depending on the subclasses they have embedded, and then we could really come up with this simplified field model where you only have one value per each magnitude, and we have a converting function that can just get a full standard field model and then get the equivalent one like let's say 1 dimension per magnitude value of the fuel simulation. So that's how we resolve the fuel modeling. Data simulation, that's an optimization process. So you need some cost function or metrics in order to optimize it. And what you have when you have a front spreading, you have the initial perimeter, you have your real observed front, and then you have your simulated one. So you can compute the different areas, subtracting the initial front. So like you only get what you are simulating, and you have different topological metrics. We have used all of them. Here I'm going to show a source and a second as a metric. Then you get your cost function, and you have to optimize it for all the isochrones, let's say all the fronts that you have in your input data. So that's the right part of the slide. So then what can you deliver? Then you deliver a better forecast. So the blue lines are the forecast, and the red lines is true fire after some time. So what you are saying gonna happen, then it's closer to what is actually happening, and or we believe. So I'm gonna show you if we reach it or not in a study case. And we hope this can be delivered easily through like cloud platforms or cloud connected platforms to the emergency responders that are down there on the terrain. So just an overall view of the model. We have this first estimation of these invariants, those parameters that we don't really know exactly. In our case, we have 7 of those. So we have fuel moisture, we have moisture of extinction, oven dry fuel loading, surface area to volume ratio, wind direction, wind speed, and fuel depth. So those you have to guesstimate at the beginning. You input those in the model. You also input digital elevation model. You also input the first isochron, so the first known isochron of the fire. So you get your simplified model, you run this optimization process, and then you really capture which are the values of those parameters that really better reshape your observations, and then you launch a forecast for this. All of this has been implemented. It has been implemented in a user graphic user interface. That's what we call QFire, and it also has this first edge detection or like front identification algorithms embedded in it, so it can help you run all over the process. An important feature of this simulator is that it also has this topographic wind embedded. That's the software that actually calculated this. It is a Wind Ninja. It's called Wind Ninja. It's developed by USDA Forest Service as well, by Fort Hoover and Beth Brother. And it's a great tool because you only give like let's say one main wind speed and direction, and it gives you back the really topographic interaction of it, so you can see the direction and the magnitude of this wind. So that's a really great tool. The only problem is that it takes quite long to give you the answer. It takes about 10-20 minutes in an 8-core machine to give a 800 by 800 mesh scenario. So you have to embed some time here, and if you put this this software in a data simulation process, since you need to optimize it by rerunning your simulation, you cannot run like 100 simulations, 1,000 simulations, because then you multiply 20 minutes by 1,000 and it's 20,000 minutes, and you don't have time to perform your simulation. So we did something to speed up those simulations, and we based on the idea that we could interpolate some pre-run base maps, so wind maps. So we imagine we have 4 base maps. At the beginning, we interpolate them, and we say, okay, we can deliver you your wind map for your specific direction and speed, given that we have 4 pre-run wind maps. We test this tool, and it worked pretty well. So we were not far along. Like the accuracy was within 10% out of the true answer from Wind Ninja. So we were really close to Wind Ninja, even though we were taking 1 second to deliver the wind map instead of 10-20 millisecond that will take normally to Wind Ninja. So we developed this in order to implement this wind modeling into our simplified model. So now let's go for the case study. That's a fire that took place in 2014 in Vall-llobrega. That's north here in Catalonia. It was a winter fire, so it was month of March, but it was after a large drought, so it has been 3 months without raining, and it was an important one because it always hit a little bit the wild and urban interface, as you see there, picture on the right. It burned more than 350 hectares and lasts for more than 24 hours, and that's 2 images of the fire. As well, it was reported by the fire service that there were a lot of dead combustible, 10 hours, 100 hours like large combustible lying under the tree canopy, because it has been a snowfall some years before that is rare in this region, so a lot of trees had fall and were dead by this time. So that was a fire evolution. The fire started there on the red star at the top, and at the beginning there was a north wind called Tramontana here situation, so we had like a large spread towards south, and then these yellow spots you see, those are reported spotting. So we see already that after 2.5 hours we already have a lot of spotting, and it was reported that the main fire spread driver was spotting. So we took the first 2 hours and 30 minutes for validation. That's this first area there, because our model does not capture spotting yet, so we didn't want to like see how the model works with spotting, since we don't have a spotting model model embedded. So we get the 2.5 hours for the beginning, and we took, since the only reported fire data, like fire spread data, was this last fire scar, we didn't have like timeline isochrones to validate our model, but we did have a far side simulation conducted by Llorenç Castell that was validated towards the data received by the fire department that responded to this fire. So that's a far side simulation already properly calibrated by all the adjustment parameters for the first 2.5 hours. So those are 35 isochrones spent 5 minutes each. So that's the weather data available by the time. That's from the MeteoCAD service. That station that was 10 kilometers away from the fire, and you see that by the fire starting, there was a strong wind from north, and that's the air temperature that drop afterwards on the night, and the wind was blowing from north at about between 5 and 7 meters per second. So that's the input data we put as a first estimation in our model, and for the field modeling we put as well the available data that like the fire service will have, like saying this, which Rothermel field is this. I'll say it's Rothermel field number 10, 15. We input it here, and we got this reduced model as we developed in our simplified field modeling, and that's far side isochrones again. So then we suppose 3 different simulation isochrones simulating scenarios. First one, we only simulate 5 fronts, step 5 minutes, so that's 20 minutes. Then 10 fronts, that's 45 minutes of simulating data, and then 22 fronts, that's 11.5 minutes of simulating data. So those are different scenarios, considering that we are in a different steps in the fire, and we input the black curve is the true or the ground truth. The green one is the first one, so with the most adjusted data, that's the first one we have in our simulation, and then when we adjust it, we can really reassemble the observations in the 3 cases. Once we have this, we can launch the forecast, because we have captured the value of these 7 parameters we are optimizing, and those are the results. The first one is for the 5 simulated fronts, so then we have 29 fronts left, so that's 140 minutes. Then we have 10 simulated fronts, so we have 24 forecasted isochrones left, so that's 150 minutes of forecasting. And last, we have 22 simulated fronts and only 12 left fronts, so that's 55 minutes of forecast. And we see that we resemble with great accuracy what the fire was actually doing afterwards. If we look at the metrics, that's this Sorensen index I was showing afterwards, we see that the blue line is the case when we only simulate 10 fronts, and we have a good accuracy of 150 minutes for 150 minutes, but we have a lower accuracy than if we simulate more fronts, let's say 10 fronts, where we get a larger accuracy, and if we finally simulate 22 fronts, we have even better accuracy. I haven't said, but this index, if it gets the value of 1, that's best fit. So lastly, we can also have the value of the actual parameters. So we optimize this value, and we can give this back to the fire responder. So the wind speed may not be 5 meters per second, but 7 or by 4, because that's the real speed that the model is capturing. And we have a really fast performance. We can run this these cases, 5 front simulated, 20 front 10 front simulation with WinNinja in it, with 150 seconds, 250 seconds in a normal standard workstation, so i7. So, concluding remarks, we have developed a data simulation framework that extracts the key parameters of a fire, let's say of some phases of fire, because that's not a spotting fire, it's a wind-driven mostly and some terrain-driven fires. We also proved that simplified wildfire spread simulation can resolve some phases of the fire. That was already proven in the field, but we also saw it here. System can adapt to different available data, so we can tweak it so we capture extra data on real time. So if we update the metadata, we can put it in the system, and we have positive time lead time. That means we can deliver the forecast to the emergency responders in a fast way. So overall, it's a promising tool to help emergency responders in order to conduct their work in a safe way. And the work in progress is to challenge this tool with real escape data. It's hard to find real escape data on an emergency because it's not the primary goal, so it's hard sometimes. And to be implemented all the system in a full automatic way. Actually, it's semi-automatic way, so we really want to implement it full automatically. And thank you.